Hello, everyone. Today I'd like to talk about more eye-friendly VR, hopefully. And we didn't find finally an answer how exactly bright it should be, but what we actually find out in the cooperation with our company partner IRYStec is that it's way too bright, actually. So yeah, just to illustrate that point, we all know this meme. But a more accurate version of it will be like this, actually. Exactly that led to a number of threads online with the question, how do I make my HMD less bright? Because currently the producers of the HMDs actually disabled all the opportunities for the user to control the brightness and limit it to a limited set of settings. So we thought that this is something interesting to look into. And the problem is well known, actually. Those who use phones, projectors, know that the brightness of the screen should match the brightness of the environment. And actually, the display industry is using a room light setup right there, cannot match well, to calibrate the displays. But in a lot of cases, we're using the displays in the wrong light settings, which in case of computer screens causes computer vision syndrome with all the unwanted things. Someone cannot sleep at night because of the blue light emission and so on and so forth. And when we think about the HMDs, actually our eyes are watching what we want to show them in the HMDs, but they are not working at the room light. They are actually in sort of a twilight where not just the cones are working, but also the rods. And for correct representation of the image that we want, we need to correct for it and show the more kind of precise information. So are there any standards for the displays in the dark? Not really. And the best we could find actually was a recommendation of the Society of Motion Pictures and Television Engineers in US for the movie theaters. And what they said is that the peak luminous intensity for the screen, for the completely white screen, should be no more than 5 candelas per square meter. And if we compare that to a typical brightness of the displays or typical brightness that we measured after the lens for the HTC Vive, that's a lot brighter. So we can see that there's a full brightness. This is a default setting of the HTC Vive, and it's quite close to the display. It's almost 200 candela per square meter. And there is also a night mode, which one has to enable manually, and this is 63 candela per square meter, and it comes with a slight tint of yellow or color overlay. So that brought us to ask a couple of questions, and one of them is, can we use an HMD with a much lower screen brightness? If yes, how far we can go with lowering the brightness? And what's going to happen with, will that impact the power consumption? Can we successfully compensate for the information loss on the dimmed display, because we, the sensitivity is sensitivity, but still you lose some small details. And maybe there will be an impact on the cybersickness. And maybe there will be also, some people will assume that there will be a impact on the task performance, for example, a visual search task. So we set up 2 Vives, and in one of those we put the anti-filters, because there was no other reliable way to actually control the brightness in this case. So we have some films, the left one over there. And we tried the 5 candela per square meter. Fortunately, the combination of the anti-filters allowed that. And it turned out quite bright, so we could go lower. And so in the end, we ended up with a double anti-filter with density 1.2. And we went below 1 candela per square meter, which was dark, but not as dark as you think. So it was quite usable, and we decided to correct for that setting and see what happens. So we ran a user study. And for this user study, we selected the task of the search the difference because we didn't have the real-time correction algorithm to run for the full-on 3D environment, so we did process the textures. There we used 2 puzzles. In each puzzle, there were 50 differences of different types with a color change, inserted objects, different sizes of the difference, where our participants had to point and click and to mark the difference. And to compensate for the 2D content, we allowed them to move like they would normally move in a full-on VR setup, walkable setup. We positioned our puzzles a little bit at the angle so that they perform a lot of head rotations, trying to actually induce the cybersickness on them within the limit of 15 minutes because we didn't want to run a user study for longer than 1 hour. The content was adapted for the mesopic vision, following the algorithm suggested by Vanat and Mantiuk in 2014, the SIGGRAPH publication. And there were 3 main steps that were done. There was first a global contrast retargeting, then the local contrast retargeting, so there are Laplacian pyramid, different depth that has to be applied, and then the local color retargeting according to inversion mesopic color appearance model. What we found out is that the standard algorithm that works on the phones, on the screens, performs slightly different for the HMD, and we had some areas that were oversaturated in terms of color. So for that, we did a short adoption of this algorithm by lowering the number of details at the local contrast retargeting step. So you can see the after effect. I think here is almost a mesopic vision kind of domain, so both of them should look pretty good, but the left one might look a little bit over-sharpened to you. But at the lower brightness, that would look exactly like the original. All right, so our experimental design involved 4 conditions, 2 default ones and 2 dark ones. One was the baseline, and one was the one where we compensated for mesopic vision and the dimmed screen. We decided to have 3 independent groups. In each group, participants experienced the compensated mode and one of the other modes, depending on the group they belong to. And to ensure that there was no bias, we counterbalanced the condition sequence presentation and also which content and which condition was presented. So the procedure of the experiment was as follows. They signed the informed consent, got instructed, fill in the pre-questionnaire for cybersickness, some general questions were also answered, performed the task 1 for 15 minutes, fill in the post-questionnaire for cybersickness, change the HMD if necessary. So if they had 2 dark conditions, obviously they didn't have to do that. And then evaluated the first condition while adapting for the new light situation, performed the task 2, fill in the second post-questionnaire, evaluate condition 2, and then answered a question that asked them to compare directly condition 1 and 2. So we had a total of 36 participants, 20 male, 16 female, aged from 27 to 52 years old with a mean of 34. 21 participant was completely naive to the VR. Only 1 participant actually had an HMD and used it every day. And majority of the participants had played the game before. So as you can see, there was a lot of head rotations involved, and users actively used the possibility to walk around and adjust their chair position on stand up, sit down, do whatever. They felt there was no learning effect, no effect of the content used. As for the task performance, the difference turned out not that striking as we expected. They found very small differences pretty much as well as in the full brightness condition, also in the dark and non-compensated one. So there was an average difference of 4 differences found. Night mode, surprisingly, outperformed significantly the compensated mode, while the full brightness had only a trend for significance in this case. But the dark conditions between themselves were not so different. From the experience evaluation, we found out the following. All the conditions were rated as quite comfortable, but they also needed to be all of them sharper, which has to do something with the screen resolution probably. Then there were no issues with finding changes of the colors on our puzzles, and no one wanted to adjust the overall color overlay on the screen. So totally ignored what was going on in the night mode. But the night mode was rated a lot higher, unlike the full brightness, in terms of better contrast and better ease of search for the differences. And of course, the dark conditions needed a little bit more brightness, which our participants indicated. From the cybersickness, we surprisingly didn't get much. So we decided to calculate the subscales and see if anything comes up there. It didn't. So we ended up looking at the individual symptoms, and we found out the following. That the dark mode without compensation seemed to cause a little bit more stress, as salivation is one of the markers. The night mode with the yellowish color overlay had a little bit more fullness of head, which might have to do something with the circadian rhythm, because of more yellow is associated that there will be a sunset zone. Surprisingly, the compensated mode had a little bit more blurred vision, which we didn't find any explanation for. The experimenters didn't see more blur, but somehow. So we will look into it. And as this was a post hoc analysis, this has to be addressed in a little bit more details later. As for the direct comparisons, we can see that again the night mode was heavily preferred, while the full brightness seemed to be not so comfortable or equally uncomfortable with the much darker conditions, which we found interesting. And the compensated mode was preferred to the dark mode, and there was a large bias in terms of that our participants thought that the brighter conditions are better, cause less eye strain, and would be better for the long-term usage. But in case of the eye strain, actually, we had the cybersickness questionnaire that absolutely didn't support that claim. So to summarize and to answer our questions asked in the beginning, can we use the HMD and the lower brightness? Yes, we can go below 1 candela per square meter. It's 180 times less than the full brightness. And the power consumption will be lowered around half of what we have at this brightness, according to the data we could find. We can compensate for the mesopic vision and for the lower brightness of the screen, but we have to invest a little more in modeling the HMDs light situation, because it has 2 chambers and the lens between them. So the current algorithm is not exactly suitable, yet it works. In terms of cybersickness, there might be some effect, but maybe it will be more prominent when we have the compensation in place, and other parameters also have to be taken into account as the confounding factors, which might not be exactly the cybersickness effect, but rather their own. And finally, the task performance according to the actual measures, was not as impacted as one could expect, but users still thought that there is a big difference. And for that, I would like to thank you for attention and also say thank you to our colleague Rafał Montiuk for measuring the brightness of the HMD for us. Thank you.
Thank you. Actually, we are a little bit running out of time, but if you have any question, please. Yes.
Yeah. Do you have any intuition on like the user preference versus like the scene, the environment, whether it's a bright environment, whether it's a dark environment for the user?
I didn't look into it, to be honest, but I guess it also has to address somewhat, you know, so if you have a sunny scene, that probably the super low brightness doesn't work that well. But for example, if it's, say, a horror game, it's suitable and it's going to be a lot better, actually, because you have the lower luminance, the most lower luminance, actually more black than everything else, so you have a little bit better atmosphere. So maybe we also should address that.
Mm-hmm. And a quick follow-up, do you think this extends well to HDR displays?
To be honest, I would like to see an HMD with the HDR display. I would probably look forward, but possibly, yes. I mean, why not? I don't see why not.
Thank you.
Thank you.